Time for our last session of this track, which is Neural Networks from the Ground Up, presented by Frank Lavinia. And everybody in this area knows Frank for sure, but for those of you coming from out of town, Frank's uh, expert in all things technical, and so we're very thankful to have him, and I will hand it over to him.
Well, thank you for that very kind introduction. Thank you for saying that I'm well known in the area. I really appreciate that. Here are some URLs that I run or co-run. Obviously, there's franksworld.com, which just turned 26 years old. Yes, 26 years old earlier this week. I have a podcast that's about 4 years old called Data Driven. And I have another podcast whose URL is not here, but I'll talk about it in a minute. So I originally wanted to call this talk, neural networks. What do they know? Do they know things? Let's find out. As a callback to the Netflix show BoJack Horseman. Don't worry, there is a one Squid Game reference in this talk. I did update it, but ultimately, it's kind of what we're going to get into, kind of the fundamentals of neural networks. Now, I did want to set kind of these expectations. It's not really going to be a lot of code in this because this is all conceptual. You can easily find code to run a neural network. What I wanted to do is I wanted to explain kind of the fundamentals that are at the base of this. So the other thing is that not that long ago, anyone that got really fully understood a neural network basically could drive whatever car that they want. Hey, it's on animating. There it is. So I just wanted to set that expectation. If you want to drive a car like that, I suggest getting into NFTs, but that's just me. I did mention that I have two podcasts now. There's obviously Data Driven, which I launched with Andy Leonard a few years ago. And last year, I launched another show called Impact Quantum about quantum computing, podcast for software developers. And we just started our second season about a month ago. And with actual guests and industry leaders, turns out finding a quantum computing expert is hard. Also, I launched another streaming service, actually, in the lines of Pluralsight and LinkedIn Learning. It's basically going to be just focused on data, and we call it creatively the Data Channel. You can watch it on Roku, iOS, Fire TV, all sorts of devices. I'll make sure that I mention the coupon code a little later. Now, this I don't get a coupon code for, but this I really recommend this. This was an edX course, professional certificate in deep learning. It was offered by IBM. You don't have to take all 5 courses, but there's definitely kind of when I took the neural network course, how neural networks actually work. And, getting back to that, for the last 10 years, we've been talking about, the AI future is coming. The AI future is it's on its way. It's like imminent. But I would say now in this day and age, the AI future is already here. And we live in a time that is largely defined by algorithms, and artificial intelligence is part of those algorithms. Strictly speaking, machine learning it uses statistical methods, but we're going to be focusing on the type of methods that use neural networks, which is kind of this self-learning, self-teaching artificial intelligence. So, computer vision is really kind of one of these practical use cases. And if you see here, this is from the Microsoft Cognitive Services Toolkit. Again, not a shameless plug because I don't work for Microsoft anymore. I actually work for Coverse, and I'm happy to talk about them. But basically what this is, it was given a picture of me. What does it say? The description is a man wearing glasses and smiling at the camera, and all sorts of other metadata in there. It even did the OCR on that word fresh connection, and it read the text on the wall. Another technology that's gotten a bit of publicity of late is deep fakes. There's actually a YouTube video here called Full House of Mustaches, where they basically take all the characters' faces and put Ron Swanson's face on it. Here's another example. I think that's Steve Buscemi overlaid on top of Jennifer Lawrence. And here's a little more nightmare fuel for you. Let's see if I can see the chat window. I can't see the chat window, so if you have any questions, just raise your hand. But ultimately, all of these things are powered by neural networks. And if you're like me and you really want to understand how these things actually work, kind of at the core, kind of fundamental level, you've probably come across a diagram or animation, something like this, right? Where they kind of show this weird mix and of sticks and circles and tells you like, hey, this is how it works. But I've never really sat well with me. I kind of have an inquisitive mind. Sometimes that gets me into trouble, but I couldn't just take where they talk about a deep neural network. And this is kind of the explanation. Well, we use the neural network and this is how it worked. And that, obviously there's a lot going on there, but what's going on here? It doesn't make any sense to me. How does this structure work and why does this structure work? And I was never really kind of, satisfied with the typical answers. And that was always kind of my reaction. Like, what? Well, how does this work? So I like to pull a line from Arthur C. Clarke, where basically any advanced technology is indistinguishable from magic. So, but this isn't magic. This is math. And this, I'm going to show you how this works because it's actually quite incredible. All right. So neural networks or artificial neural networks are inspired by biology. And you may have heard that before. And ultimately, it is based on how, hopefully you have one of these between your ears, and all of these, this brain consists of many, on the order of billions, and each one of these connects to another neuron. You can, and not just more than one neuron, so you can actually have trillions upon trillions of connections. And ultimately, this is what a neuron or nerve cell looks like. You have the dendrites, which basically kind of take in the information from other neurons. You have the cell body, or the soma, and then you have this axon, or this which is protected by a myelin sheath, and this basically has terminals where it connects to other neurons. Now, the first person to discover this, or basically was a scientist, Santiago Ramon y Cajal, and he basically was an artist and a pathologist, and he was the first person to see and document a neuron. Now, this sounds pretty gross. He took slices of brain tissue and basically stained them with the same thing that they were using early for photography. And this is what he discovered, that this is what the brain was made of, cells that look like this. Now, if you a little familiar. So ultimately, this is the idea of mimicking kind of biological systems with algorithms, with code. But still, how does this work? How do you get from the point where, given an input of a picture of a dog, you have all these hidden layers, an input layer and an output layer? Now, again, I'll say artificial neural networks are modeled after biological neural networks. And like biological neural networks, they have this notion of they fire or they don't fire, or they pass the message along or they don't pass the message along. Turns out there's mathematical functions called yes, I see a hand went up. Stan?
I just wanted to. We're losing every so often. We're losing you for about 2 or 3 seconds of audio. I thought it was just my connection, but somebody else mentioned it in chat. So
All right.
I just wanted to.
I'm going to turn my camera off in case that's the problem.
Okay, sounds good. I just wanted to alert you to it so that if there was something, you could adjust. Okay, thanks.
No problem. All right, so hopefully this is still working and you can hear me.
That did not fix it.
How about that? Is that any better?
I can hear you now. Yes.
All right. So my fancy microphone is on the fritz today. All right. So, and Teams just told me that my microphone wasn't working. That's pretty funny. All right. So the pros are you get amazing results out of these neural networks. Cons are you get a lack of explainability, meaning we actually don't know how they come to their conclusions, believe it or not. And we'll see that kind of here. That's kind of counterintuitive. So there's a whole notion of pushing AI algorithms to be more accountable and more discoverable and more explainable. Well, that is not it's not trivial to do that with a neural network. They are computationally expensive and they get very complex very quickly. So this is basically what an artificial neuron would look like. And what you're seeing here is you have X1 and X2, right? These are your inputs that go in, and these are the weights that go in. And each one of these has a weight, and we'll kind of look at the formula in a little bit. That should make a little more sense. And this is the bias gets added to it. Ultimately, inside of here, you get the Z, which is essentially the first input times the weight that's associated with that first input, plus the value of the second input times the value of the first input. I'm sorry, the weight associated with the second input, and then you add the bias to it. And then the activation function then gets passed, and then basically the output of that artificial neuron is what gets sent forward. So just like a neuron, it gets in information, does something happens inside of the cell, and then on the outbound thing is, it either fires or it doesn't fire, it either propagates a signal or does not. And each one of these functions, the most basic one here is called a sigmoid, has nothing to do with Sigmund Freud, but ultimately it's the idea is that it compresses kind of very large numbers and very small numbers into a space between 0 and 1. Now you're probably thinking right now, hey, that's a lot of math. What's going on here? Well, there is a lot of math, but it's not complicated math. What's actually happening is another way to look at it is like this. You have, in a traditional algorithm, if you pass parameters to a function or method, whatever your language or choice calls it, you typically have one or two knobs. And for those of you that are too young to remember, that's what it's called a radio. It was kind of like an iPod or an iPad. It would stream music live off the airwaves. Now, if you think about it like this, and this was the aha moment for me, is that functions would typically you would realistically never have a method or write a method that had more than 5 or 6 parameters in it. But what if you could have a parameter that had a lot, and I mean an exponentially amount more knobs and dials, as it were? And ultimately, that's kind of what a neural network is and how it works. And we'll see that in a little bit. So MNIST is this famous experiment. This was, I think, originally a challenge that was issued to the scientific community by, I want to say, the Postal Service, and this has since become known the MNIST data set. It's kind of the hello world of neural networks, and it's essentially a large data set of handwritten digits. 60,000 training images and 10,000 testing images. So you basically, what you do is you point your neural network, or you point the code at it, and it will go and it will basically compute what this digit is. So if you were to think about it from a traditional kind of algorithm way, what does a 2 look like, right? A 2 has, this loop here, and then sometimes there's a curve. Sometimes, though, there's not a loop in it. So 2 is a really kind of complicated number in that sense. So traditional algorithms never got really much better than 50% kind of effectiveness. But it was the neural network approach here that got to the point where it was in the 90s. And in fact, you can actually get to 97, 98% accuracy there. But ultimately, what they are is they are a grayscale images, 28 by 28, and that would equate to 784 pixels, which essentially would become 784 input neurons. The second layer would have 32 layers inside that neural network. So you would have the input layer, the first layer would have 784 inputs, and then the second layer would have 32. And all of these values would collapse down to one of these 32. And then finally, another 32 layer, and then it would get to 10, right? The value of 0 through 9. Ultimately, if you did all of this math, what would happen is that in this one number, in this one kind of run through it, there are 26,500 and 6 adjustable parameters. So think about that. Think about the complexity that this actually gets. So you get back to this idea of, let me roll back, is that, kind of traditional programming, you have the volume, you have the tuning, and that's about it in terms of what options you have to parameterize it. But here you have something closer to 26,000. So that's basically it, kind of in a nutshell. And you can recognize numbers. Here's the obligatory updated meme for Squid Game. So with so many parameters, you can do just about anything. And this is basically, you'll hear that, GPT-3 had, billions of parameters. I think it was 4 point something billion parameters. And now you're probably wondering, like, hey, Frank, if this is so great, how come this wasn't done before? Well, it was done before. A lot of the early work into artificial neural networks dates back to the late 70s and early 80s. But we basically ran out of, these are very computationally expensive. So to just run through that one type of process, you had to do 26,000 calculations. Now, if you were training that times, say, the 60,000 images, then that's 26,000 times 80,000, but you have to do it more than once. You have to go forward propagation and back propagation. And I'll explain that in a little bit. But this is the type of work or accuracy you can get in terms of this. It's all about reducing those errors. And if you look here, the error rate here, based on, there's a clear winner here in terms of deep neural networks. And convolutional neural networks are a different type of neural network, but you'll see kind of like the traditional approach of using a linear classifier, kind of like basically this line here. Once you see deep neural network, and that's just a 2-layer. So it goes to 784, 800, and then 10. You'll see that the error rate drops dramatically once you kind of get into that space. Now, I mentioned training, and this is basically the stuff that's computationally expensive. Once you train a neural network, you can deploy it on very low power devices, because ultimately that's where most of the work is. So here we go. So this is a great visualization by 3 blue, 1 brown. And then basically what we're seeing here is it's taking all of these pixels in an array, and it's spitting out the values of intensity, right? So it's basically, in this case, it's going to be between 0 and 255 to represent a grayscale. So that's 784 pixels. That will then get reduced down to this layer here. And then each one of those lines represents the strength of the connection. So what happens is that that's a 3. And then what the first neural network approach comes out with is probably going to be utter trash, as he said. So then what you do is that it really should be, this should be it, and then you figure out the difference, the delta there, right? And then you go back and you back propagate it, where you basically say, okay, well, how would I go back, and what knobs and dials do I have to change here to get the answer here? What knobs and dials do I have to change here to get that pre-intermediary state? And ultimately, that's back propagation. When you go and then you go forward and you test it again. So you basically have to rerun this calculation that hundreds or thousands or even hundreds of thousands of times. And this is where you hear the term gradient descent. Ultimately, it's the idea of getting the least amount of errors. So the first time you run through an iteration of a neural network, training a neural network, that is, you ultimately want to find where the knobs and dials produce the least amount of error. Now, you can't make everybody happy. So remember, if you perfectly tune it so you get the answer 3 all the time, you may have unintended consequences by throwing other results off. So that is basically kind of this idea of gradient descent. Now, you'll see that the first time you run a network, maybe you want to find the lowest value, and where this means the lowest cost, or mean the difference between what your actual values are versus what you want, and then you adjust your weights to it. So if you remember, every input had a input value and a weight to it. So you basically, I like going back to this picture because it does explain it pretty well, is that you want to go back and adjust these knobs and dials just so it's right. And this is a great analogy because you don't need a sound engineer. Once the room is set up and all the acoustics have been set up and tweaked and finalized, you don't need a sound engineer to speak into the microphone, right? Because all that work is done up front. So it's kind of like that, is that all the work is done in the training side of things. Now, here's where it gets crazy. You can imagine finding the lowest point in a graph of in as many dimensions as you can imagine. So this could be 3D. So this is what the term gradient descent means. You want to find the least value, the lowest value of a graph. Now in this graph, it's pretty easy, right? You can find that graph without any trouble at all. But what if, and I'll get my pen, unfortunately is tied to another monitor. That's okay. Right? What if the graph looks something like this? Now, you and I know this is very clearly the lowest point. But how do you find that lowest point? What if you basically, how this works is you keep going, you search through it, and the distance, well, it won't let me draw. So it won't let me draw, but ultimately you keep going until you hit this minimum. And then when you hit this minimum, this is called a local minimum because it is a low point, but it's not the lowest point of them all. So that's kind of the challenge here. As a side note, this is what makes quantum computing exciting, is it would find the absolute lowest value on a curve just about instantaneously. But I don't want to get distracted with quantum. Very easy to do. All right, so I want to show you a demo here. That was put together that visualized this, I think, fairly well. Again, this is the MNIST data set. And what you're seeing here is I'm going to draw a number here. I'll just draw a 4. And what you're seeing is the values. So the first guess was a 7. And the second guess was a 4. So let's see if we do that. That's interesting. All right, let's try 1. All right, so the first guess was a 1. And the second guess was a 1. The second guess was a 6. So what's interesting about this is that what you're seeing here on the top layer, come on. What you're seeing here on the top layer is the grayscale representations of the image. And this will trace back through the neural network how it all connected and how those nodes and what the weights and biases are. So if I'm going to show convolution level 1, oh, that's a convolutional network. That is a slightly different approach. Hang on. This is a great site, by the way. All right, he's got a lot of stuff here, more stuff than the last time I looked at the site. Let me show you this because this is another way to look at it. And this is all done in browser. You don't have to install anything. It's done by Google. And ultimately, what it's trying to determine, given this problem space, I'll pick a simpler problem space, which is orange and which is blue. And the key here is the ability to determine which is it. And it's going to learn the difference. And what you'll see here is you're going to see the loss. And I'm just going to run this. Now I'm going to leave it at the default settings, right? No regularization. I'll pick a sigmoid. Learning rate is 0.03. So I'm going to run this now. Let's see what happens. So I'm going to pause it real quick. You'll see right away the loss at first, because everything was kind of set at random, was pretty high. And you'll see that right now the graph dropped. So let's keep going, gets a little lower, and eventually you'll see it'll just kind of snap in place, like it just kind of gets it right away. Or supposedly, it's supposed to. All right, so let's give it to about 1200. Let's see what happens. But you will see it does kind of stall. right? It gets the idea that these are where the blues are and this is where the oranges are, but it does these false positives or false negatives here. So each one of these visualizations, you get to see how it does this work. And the width of this represents the weight and the strength of the connection. You'll often hear the term neurons that fire together wire together. And you'll see right there at that moment, just about at 1200, I was getting a little worried there. Usually it takes about 1100. You'll see it figured it out. It got it, right? So now our loss is 1%. And it basically, this is, I can keep this going, but you'll see it'll kind of plateau at some point. Now, your first thought is probably like, hey, Frank, well, that learning rate was so slow. Like, why don't you make it bigger so we can go faster? So let's see what happens. And to be fair, I'll give it about, to about 1200 this time. But you'll see that the error rate dropped right away and then it got really bad. And the reason for this is because what's actually happening is that, where did we go? You think back to here, the error rate is how far you go in adjusting your settings. So for instance, in this example, this was it went this far into there, it went this far into there. If the learning rate is too fast, what'll happen is it'll go here, it'll overshoot it, right? It won't be able to get that granularity. So it'll go from here to like here, and then from here, it'll adjust to here. And then from there, it'll adjust to here. It'll never find the true minimum. It'll always dance around it. And you can see right about now, yeah, we're at about the same and we have no progress there. So this is kind of an art and a science. If you pick it too low, too much granularity, so let me start that over. You'll see that there is steady progress, but it's really slow. So there's always this kind of this tension in neural network design of it's not quite as easy as it sounds. You know what I mean? You just can't just point the computer at a problem and it'll go through it. There's very interesting design considerations that go into setting these parameters. And you may think, Frank, what a big deal, right? I mean, like it only takes a few minutes. Yes, in this contrived little example, this is just 1200 iterations or epochs. But in real kind of, keep in mind this has 2 hidden layers and only 2 values going in. You can imagine if using the example, an extreme example of GPT-3, that they had billions of parameters. So that's not just, I mean, that was, depending on who you talk to, said $5 to $12 million worth of compute time. So these decisions could have very significant consequences. So for instance, I'm now on my 1300th epoch, and I'm not really anywhere close into coming to any kind of decision, because you look at how far off I am, I'm orders of magnitude slower. So it just happens to be that each neural network problem, each type of classification problem will have a certain sweet spot. So that kind of answers the learning rate aspect of it. But let's talk about this here. So I think originally this started with 10H. So let's just say, let's see how long it takes. I'm going to use learning rate back to the default, and let's see how long it takes to learn. All right, so you'll see it does a pretty good job, and I'll stop it right there. That's 10 times faster. So each one of these functions has different connotations too. Sigmoid is kind of the old school, or was kind of the original type of, was the first function that was really out there. That was the one that we saw the formula to. There's tangent H, and then there's rectified linear unit. This is kind of, I think, one of the newer ones. And each, again, no one's really better than the other per se. It's just that each one of these has a certain consequence to it. So let me run that again. So this is this is rectified linear unit. You'll see that it does a pretty good job in even less time. Now, is it perfect? No, neural networks will never get to 100% reliability. In fact, I can guarantee you that if somebody told me that they had, 100% guaranteed answer results from their neural network that they're lying or grossly misinformed. So let's add, let's take this problem to the next level here. Let's do something difficult. All right, so I'm going to pick learning rate of 0.03. I'm going to keep using ReLU, and let's see how many epochs it takes for it to figure this out. So what's interesting about this, and this is what always fascinates me, is that it just keeps turning and chewing on the problem until it gets an actual answer. And it just when you think it may have hit a stall, it will actually come up with a decent result. Now, keep in mind, there's a lot of things I can do here, but I haven't done them yet. I've just tweaked kind of 2 parameters in this. And what's interesting is I'm not really running this, right? This isn't coding kind of in a traditional sense where I'm slinging code. I'm slinging code to tell the computer how to approach the problem. So in a sense, I'm kind of, instead of being in the driver's seat, I am telling the driver where to go, so to speak. So you'll see it's chewing on it. It's getting there. It's hitting some glitches. It will eventually get there. I've seen this work in about 4,000 epochs. But you'll see it kind of gets hung up. So what's happening now is it's going through, it's doing the forward propagation, figuring out what its prediction is, right, in each one of these. And then the weight of these represents what it's learning and what it's adjusting. And if you look closely, you'll actually see some neurons kind of learn. So you'll see that it seems to have kind of plateaued. So let me do this. Let me add a couple of middle layers, and you'll see now, effectively what I'm doing is I'm adding more knobs and dials to get maybe a better resolution here. So I'll bump this up. So I have 6, far, and 5 and 4. So let's see if this does anything. This learning rate, I'll keep to that. I'll keep the ReLU. Let's fire away and see if we get any better. So now this is positive. You see that test loss and the training loss is dropping. And you'll see the animation it's getting there. And I always worry because, I literally don't know how this is going to work because each time it's going to run a little bit differently. This is not strictly deterministic, so to speak. Any questions at this point while I sweat it out? I see somebody might have their hand up. Alan Jacobson has his hand up. Do I unmute him?
Yes. Hold on.
Do I have the rights to do that or allow my? Looks like I do. Alan, you can speak.
There we go.
No question.
Hello?
Yes, I hear you.
Oh, thank you. Hey, so my question is pretty simple. How do you know when to add an extra layer versus adding more neurons to the existing layers?
It's really kind of trial and error, honestly. There is work being done into that. Typically, you want to add more layers. That's typically you get more bang for your buck if you add just more layers. And if you look at the screen now, look what it's doing. It's kind of figuring it out, and what's fascinating to watch this is that you are literally watching the computer learn, like right now. Like it is learning what it should and shouldn't do. And if you have kids or you've been around kids, it's kind of like a similar, much more simplified, but it's kind of interesting to see how they come to their results. And so typically, I would say in this case, if I were to start it over again, let me reset it. So we're 600 epochs. That's actually not bad for 600 epochs. All right, but you'll see that it had this weird thing in there where it got completely wrong and then it fixed itself. So let's add 2 more hidden layers. Let's go there. And it's really as much art as it is science, honestly. And it also depends on the type of problem you're addressing too, because what we're looking at here is really, it's not kind of some of the newer types of neural networks that have come about. There's generational adversarial, there's convolutional, which all kind of take a slightly different approach to kind of this original thing. The most of what we've been looking at here today, because it's the simplest kind of study, is called a perceptron. and it's based on some early work that was done in the space. But it kind of shows you how these very small discrete units of computation, when you chain enough of them together, can produce results that can outperform, you know, traditional approaches or even advanced statistical approaches. Like you see right now, it's having some trouble with it. It's also worth noting that you'll see that on this the epochs aren't going as quite as quickly as they used to because there's slightly more computations here. So what there would be, I mean, if you could do the math, it's 6 layers, 6 neurons. I don't know. It's Saturday afternoon, and I haven't had my normal amount of coffee, but you can, you can very quickly run up kind of your processing here. So you'll see it's actually doing a decent job. It's still learning. It's still got a ways to go. What's interesting to note is that you'll see that it gets completely off base, and then it seems to recover, which is interesting because I think that's, if you think back to learning a new skill, it's like you kind of learn more from your mistakes than you do from when you get something right. And you'll see it's going to keep chewing on it, and it takes about 4,000 epochs to get this right. You know, so these are all types of. This is ultimately kind of the behind the scenes of what an AI engineer would do. You know, they would, they would go through and just kind of tweak this. Like, typically at this point, you kick off the algorithm and kick off the training and then go to lunch, get a coffee, and then kind of experiment with different ways and different approaches to get kind of the answer that you're happy with. I mean, in this case, what's my test loss? 0.2. Maybe I'm okay with that because most of the time it's going to get it correct. It all really depends on what you're looking for. And if you see kind of this little picture here, is that this is what that neuron fires on. It's a gray scale of, or white to blue scale of kind of where that neuron says if that pixel is there, it'll vote for blue if it's there. And you can kind of see as you get further down, it gets way more nuanced. You'll see that the first layer is very simplistic, right? It's just basically kind of, well, if you're in this part of the screen, and here you'll see it picks out certain features. Any other questions? All right. I'm going to see if I can find, so this is a visualization of a convolutional neural network. This guy used to have a visualization of kind of the perceptron that we saw. This is what I want. So this is basically kind of that MNIST example that we're talking about. So I'm going to draw, I'll just say 3, because the talk ends at 3 o'clock. And you'll see that, its first guess is 3, its second guess is 7. So that's interesting. So we'll see that the strongest point was here, and this is kind of all the connections that were made in from there. So this here is the top, is the first layer of the neural network, and basically that's how that value maps to every one of those cells, and then we can go up here. So you can actually trace the lineage and kind of see what lights up to produce a different number. Now, what's fascinating to me is kind of what if you draw things that really have no, that is clearly not a number 0 to 9, but it doesn't, this is meant to, it's only going to recognize everything has to kind of be a number from 0 to 9. So interestingly enough, it thinks that's a 2. So what I can do here is if I just kind of just go crazy, you'll see that it's just interesting to kind of see how the mechanics of this work. And there's even ways where I can just kind of discretely come up with numbers. So let's see what that would do. That produces a 7. What would that do? That thinks it's an 8. It's fascinating because the things that you think would work don't work, but it always gets to an answer. And what's interesting is sometimes it's a right answer and sometimes it's not. So this seems to think that's a 3. Let's see if I go back here, I clear this entirely. A dot, you'll see it's a 5 or a 7. Probably because usually if you have a 5 or 7, that part of the screen is done. So let's pick kind of this corner here. Let me clear the whole thing. What does it think? So you see when these colors are that close together, those that's a heat map of probabilities. So it's actually, in this case, it's really not sure, is it a 5? Is it a 2 or 1 or a 7? And this is just picks the first two in probabilities. So let's just see if we do this. What does it think it is? Thinks that's a 2. Let's make an X. Thinks that's a 7. It's interesting to kind of mess with it. Let's check in on our old pal here. So you see, it's actually gotten pretty good. It's 0.1. Whoa, it's freaking out now. We're at 1,000 epochs, but it's still learning.
Do we have a question from Alan?
It hand's still up.
Nope. Nope.
All right, let's give this a shot. Sorry, go ahead. There we go. Always like to end a demo on a positive note. You'll see how quickly it got it. It hits that point where it's kind of stagnant, and then it reaches this eureka moment, and you'll see that it had a dramatic drop in the error rate. And that's basically where it kind of ends up. So this has always fascinated me because you can play around with this and experiment with stuff. You're not really doing anything kind of to break anything. Let's see how quickly it can get. This is a different type of problem, a regression problem. And you'll see, that learned it pretty quick. Now, if I were to take away some layers and simplify it, start it over, it may not be so quick, although in this example it is. So it's really just kind of just trial and error, and you get a feel for kind of what types of adjustments to the parameters there are. Now, moving forward, there's different types of networks that are here. There's convolutional neural networks, which basically they go through and basically examine a picture and reduce the picture down to kind of the fine edges, and it reduces kind of all the superfluous data to it. And convolutional neural networks work really well with computer vision problems. So here's an animated GIF describing what a convolutional neural network looks like. So if the bottom image would be kind of their source, the bottom squares here would be the source image, and then the top here would be the convolution. So what it basically does is it takes the average of all of those cells and it kind of iterates through all that pixel data. Another example would be transfer learning. So transfer learning works in a way that you have a network that is mostly trained, and then what you do is the final step, it will spit out an answer, right? It's either value 1, or in this case F1 through F8. There'll be more in a real example, and basically you tell it in a final layer of a bit of training. You say, well, if F2 lights up, then it's a hot dog. If F8 lights up, then it's not a hot dog, right? So what you're doing is you're basically tacking on a final layer of the neural network at the last minute. And transfer learning is kind of a hard concept to explain. So this one I like to point out is that, which one of these is the hunter and which one of these is the hunted. Now, obviously, the animal with the sharp teeth is probably the one that's doing the hunting, and the other animal that's running for its life is probably the hunted, and that is essentially transfer learning. Chances are you've never seen a dinosaur in your life, like in the real world, maybe, movies notwithstanding, but you knew that. You knew that because just nature and kind of the things around you. That is essentially transfer learning. Stan, I saw you go off mute. You have a question?
Oh, no, sorry.
Okay. So any questions at this point? I realize I'm like, the guy between the end of day and whatever, but I appreciate you sticking on and and watching. Here's my contact information. If you, I'm offering folks a deal on the streaming service, datachannel.tv. We're on all these platforms. We'll be on Android TV soon. Basically, we're going to have a lot of content on there. Right now, we just kind of have the initial start of it. Andy and Leonard and I are doing that, and if you use that code, it'll basically be $4.97 a month, which is cheaper than the listed price of $14 a month. We're kind of like Disney Plus, but for data. And then if you really want to be bold, there's the code. There's the coupon code for $47 for the year, basically. Any questions? No questions? Everybody bummed out that Saturday got rained out? Bueller.
I'm bummed that Saturday got rained out. I'm just gonna go get some sun.
I have some mixed feelings because I had yard work to do. So
yeah, well, not anymore. You don't.
Not anymore.
I heard the rain trickling out there. Well, I really appreciate your talk.
Thank you.
It's very interesting. I appreciate all the speakers today. We had Ron Dagdag.
We had a question.
Oh, we have a question.
Jeff Hanlon. So I will unmute him, allow Mike, and I think you have to unmute yourself.
Hi. I'm sorry. The CNN, the convolutional neural network, that's also used in non-neural network training, isn't it?
To my knowledge, no. I mean, there's what's interesting is that there had in the last few years has been a big burst of different types of networks. There's generative adversarial networks where these two networks will kind of fight each other, so to speak. And you get some interesting creative work on there. Deep fakes kind of comes in that world. Synthetic kind of, if you go to this person does not exist, that's basically created through a type of GAN, where they generate data. And what will happen is that the two AIs will kind of argue, hey, look, I made a face. And then the other one will say, no, that really doesn't look like a face. You should change this. And then that kind of iterates, hundreds of thousands of times. You get some interesting results. To my knowledge, convolutional neural networks can be used for a couple of uses. The one they were originally invented for was image processing. They tend to work well when you have mass quantities of data that you're trying to reduce down, right? So think about an image, right? If I upload an image, it's a 14, 15 megapixel image. That's 14 million bits or pixels in that image, and that means that for each channel, if it's a color picture, I have to deal with that many input neurons, which means, that would blow out your computer processing. So what convolutional neural networks do is that when you convolve around them, you can kind of reduce it to just, I don't want to say just the edges because that's not totally true too, although edge detection is in there, but you do reduce kind of the raw input that comes in. There are a couple of other problems I've heard it used for, but they escape me right now. What's the big innovation in the last 2 years has been transformers, which are basically best described as neural networks of neural networks. And those tend to work, those tend to be found in kind of language models. So you'll see, what's interesting is if you're doing natural language processing with neural networks, or natural language processing in general, it tends to be implicitly temporal, meaning that if I say I went to Paris and I really enjoyed my time there, right? What's there, right? Like, so that there has to relies on a callback to something that happened before. So with those, you tend to find LSTM networks, or long short-term memory, right? Because if I say I really enjoyed my time there, oh hey, can you give me the bottle that's on the shelf there, right? Well, clearly the second time there refers to something else. So it becomes, language processing is actually a lot more complicated than it sounds. So it turns out that you can do, if you string these different neural networks together, you can build something that's called a transformer. And that's kind of the most recent innovation that I'm aware of. But the big challenge that we're facing is that we're really running out of compute resources. Not really running out, but I mean, innovation in the field is starting to slow down, and that's starting to freak people out because the cost of doing all of these computations, at least at the research level, is starting to add up. And as long as the venture capital and the investment keeps coming in, that won't be a problem. But at some point, there's concerns that there'll be another AI winter, so to speak. I think people are kind of freaking out. It's too early to call it, but I mean, there definitely are kind of, we're going to hit a wall of innovation, and then there'll be more research that'll come on later. But I think these things kind of come in spurts. But there's still plenty of opportunity in the AI neural network space because these things still have to be deployed in the enterprise and managed, right? The hot term now is ML ops, right? Like how do you train a model on new data and then propagate that model down? How do you containerize these so you can run these on kind of at the edge? There's the frontier is always moving, so to speak. But that's a good question. There are a few use cases for convolutional neural networks. But what's interesting is that there's multiple tools in the tool belt now, just in neural networks. Did I answer your question?
Yes. And well, I just wanted to ask you one more, and that is like, okay, in the case of like a autonomous robot, with object detection real time, would it be a convolutional neural network or some other type of model or some other type of approach?
So that's a fascinating thing. So there's multiple ways to approach that. There's another type of machine learning or artificial intelligence called reinforcement learning. But if you're talking object detection, I would say it's probably going to be some form of CNN or convolutional neural network, possibly tied into. You can use all of these approaches together, which I think that if you're dealing with something as complicated as an autonomous, robot or vehicle, I think there's going to have to be some kind of reinforcement learning aspect, obviously a computer vision aspect. There's a lot of moving pieces there you can apply to solve that problem.
Okay, thank you.
No problem. And that's the great thing is that these are not mutually exclusive. You can tie these neural networks together, even if not like directly together. You could have the computer vision system would detect an object ahead of you, and if that object meets a certain criteria, then you could do something else, or you can train a self-learning reinforcement algorithm to do different things based on that, or it would discover on its own. I mean, this is a very fascinating, very fascinating field. Any other questions?
Okay.
But when it comes to, so in the case of like a Tesla with the autonomous driving,
right?
So that would, I presume, uses maybe LiDAR, radar, and vision. But that's all on board within the car, and those models, those would all be self-contained.
So with Tesla, what they're doing is that they're they're taking all of that data and then crunching the numbers back kind of at their central server farm or whatever. And then what they do is they take those learned models and then push those learned models. Remember, the learned models is nothing more than kind of a basically a series of settings on dials and knobs, not dials and knobs. You know what I mean?
Gotcha.
So the hard part is figuring out which one do I turn this one to, and that one to, and that one to, and that one to, right? So that's computationally expensive. Actually using a model and calling it, that's relatively cheap. So the reason why, there's a number of reasons why. The great thing about the cloud is, you can scale up when you're doing the training, and then you get this discrete kind of, essentially it's a matrix of sorts, and you can go through and it would tell you, then you can deploy that, and then basically you would just kind of pass the values that it's expecting, and then you get the answer right away. That's actually very low computational. So in the case of Teslas, there's a little more to it than this, from what I understand. But basically, what they do is this is their plan. I don't know what their lawyers have worked out some of the privacy implications and stuff. But if you drive around your Tesla for a week, and then once you park and it connects to your Wi-Fi, it will send up all of the sensor data, the picture data that it saw, everything, right, will go up, and then they'll use that to, well, hey, so and so didn't have an accident today, so we'll treat him as, a good example of how to drive. You know what I mean? And then they do that in mass. So if you do that just on one person, that's one thing. But if you can kind of do that all in mass and then crunch those numbers all together to determine, and that's basically kind of their business model. So the car isn't just a car; it's a data collection mechanism. And then once they train that model kind of off their central thing, because you would need serious compute power to process all that information. Then what they'll do is like, oh, here's the settings, here's exactly kind of what to do. Then that actually gets deployed locally on your device, in this case, your car.
Okay.
And then supposedly they have this scheme where it'll actually update all the time, like every couple of days. So it's an interesting. That is probably going to be the biggest ML ops challenge of them all, because it's not so much. The whole enterpriseization of this technology has been fascinating to watch, because it went from being, hey, look, I can build a model that'll predict our business problems, to, something changes in the field, because that's called model drift, right? You can easily imagine, economic forecast, that were made in 2019 of how a business operates. Well, in 2020, things kind of went sideways. Those models were no longer accurate. So just like weather forecasts have to constantly be updated, this is kind of the same idea. And then how do you operationalize that? How do you make that a process? How do you make it so it's more like a DevOps pipeline where, the data scientists do their data scientisting, and then the operations people can kind of take those models that get created, and then that gets deployed and kind of managed and tracked. Does that make sense?
Yes, it does.
That's actually, I think, turning out to be the harder part than this.
Yeah.
Harder in the sense of challenging, not so much like mathematically hard, but just kind of people and processes and technology.
Okay. We are at 3:00. I can let this go. I will have to drop off, but I just wanted to thank Frank and Prashant and Ron and Sam for their talks today. And I thank all of you guys for attending. Anything that any of the presenters want to share with people, post in the Discord chat. And other than that, I will let Frank continue on if he likes.
Awesome. I actually have to go, but
Okay.
feel free to hit me up. I'm not hard to find. I'm on LinkedIn, and that's it.
Thanks, everybody. Have a good
Awesome.
rest of your Saturday.
Thanks, everyone.